I wanted to first ask Ranger to sort of set the stage for us and to tell us, to start from almost a definitional point of view, what is geoengineering and why is this set of issues starting really to be discussed with some degree of seriousness at this point? What is it in the state of play of climate science and carbon regulation that might be stimulating this discussion?
Okay, and we're running the experiment tonight to see if an engineer is capable of talking without slides. Both John and I have slides that are out there on the table if you want copies of them. I thought actually I should start just a few steps even back from what you described and make sure we're all sort of up to speed on the climate problem. The sun shines on the Earth, of course, and about 30% of that light is immediately reflected back into space. And the other 70% is absorbed by clouds, by the surface, by the oceans, and so on. And of course, if that was all that happened, the Earth would rapidly heat up and we'd all fry. Somehow we got to get the same amount of energy back out into space as got absorbed. But once it's absorbed, it can't be re-radiated as light. It has to be re-radiated as heat, as infrared, you know, like a radiator radiates. And there's the rub, because the atmosphere, while it's transparent to the visible, is not transparent in the infrared. And so what happens is that the whole temperature of the planet warms a bit, and then finally it gets to a warm enough point that the amount of heat energy radiated off the top of the atmosphere is just equal to the amount that's being absorbed, and so the planet runs in equilibrium. And that's a good thing for us. This is the so-called greenhouse effect. And if it weren't for that, planet Earth would not be a terribly pleasant place to be. The two principal constituents in the atmosphere that absorb infrared are water vapor and carbon dioxide. And we have, for several hundred years now, been gradually increasing the concentration of carbon dioxide, and as a consequence, the mean temperature, or the average temperature at which the planet operates, goes up. So that's all kind of theoretical, and in the slides, one of the things you will see is a picture of a couple thousand megawatt coal-fired power plant just west of where I live, called the Bruce Manfield Power Station. A plant that size uses a couple hundred of these large 100-ton hopper cars of coal every day. And so to give it sort of a more concrete sense, a plant like that takes a couple hundred, a train of 200 cars, turns it into an invisible gas, puts it into the atmosphere every day, and we're doing that in hundreds of facilities like that all around the world. So though it's invisible, the mass volumes are quite large. The one other thing I should say about the physics or the science is that unlike conventional pollutants, unlike, say, sulfur dioxide, oxides of nitrogen, which when you put them in the atmosphere only stay there for a few hours or days. So if I stopped emitting sulfur dioxide, it would rapidly disappear, or if I stabilized emissions, concentrations would stabilize. CO2 and other greenhouse gases aren't like that. They live in the atmosphere, many of them, for 100 years or more, with the result that it's kind of like a big bathtub. If I had a bathtub with a small drain and a big faucet, unless I really close down the faucet, the bathtub will continue to fill up. And so think of the atmosphere as like that bathtub. And unless I dramatically reduce emissions by 80% or so globally, the level of concentration, or the concentration of CO2 in the atmosphere, will continue to rise. All right, that's all the science, but since it turns out many people do not understand this cumulative effect and the fact that one really does need to dramatically reduce emissions in order to stabilize concentration, I've started making a point of talking about this whenever I talk about climate issues. Now I want to talk about two other things before I turn things over to John. First of all, the word geoengineering turns out to be sort of all-inclusive. I mean, to different people, it seems to mean all kinds of different stuff. The Royal Society in London did an assessment recently. Actually, the discussion in the back of that assessment on governance builds directly on the results of the 2 workshops we ran, because 2 of the key authors had been participants in both of those workshops. And they did a very useful thing. They introduced 2 words, solar radiation management for stuff that involves changing the albedo. And actually, in a piece that we published in Nature about a month and a half ago, Nature used some phrase about sunscreens or sunshades, which is perhaps maybe even better. And then all the other stuff was termed carbon dioxide removal. And among other things, on that side, I mean, you can actually build devices to scrub carbon dioxide directly out of the atmosphere and then sequester it, that is, put it deep underground in appropriate strata. Those sorts of processes are inherently slow. They could be as cheap as $100 to $200 a ton, so they're important. They set an upper bound on what the cost of controlling CO2 might be. But they're inherently slow, and you could do them within the confines of a particular nation. I don't view them as posing significant governance issues. On the other hand, the stuff that involves changing the albedo by, for example, putting very fine particles in the stratosphere, and we can talk a bit more about how you would go about doing that, could be done at relatively low cost, perhaps 1/100th or less the cost of abating emissions, and could be done by a single state operating within the confines of its national borders. The first reason is that there's some possibility that somebody else would do it, and then if we thought that was a terrible idea, because, for example, it does nothing about the ongoing acidification of the oceans, which will probably leave us without coral reefs by the end of this century, or any of a number of other impacts from rising CO2. If we thought it was a bad idea, we need to know enough to be able to mount coherent counter-arguments. And the other reason we need to do research is to, in the event that we have a climate disaster, we know what we're getting into if we suddenly decided we had to do this, if we had 1 billion people at risk around the world, for example. And so in the back few slides of this thing that I've passed out is an argument that says one of the things the climate science community should start doing fairly quickly is figuring out a space in which they could do field experiments without any sort of international oversight or review. I think we do stuff in the stratosphere all the time, of course, and so it's not as though the stratosphere is absolutely pristine. But you don't want to have people going off and doing things that involve large radiative forcings or go on for extended periods, or for that matter, provide lots of reactive surfaces that could result in significant ozone destruction. So I think one of the early requirements for the science community is to figure out, can you define a sort of space within which, as long as you're behaving inside that space, issues of governance are not a big deal, but doing anything outside that space requires some collective agreement that it would be appropriate to do that. And at that point, I'm going to stop and let John pick up.